Okay, what we're going to work on here for the next few minutes is how to find the sum of two vectors. Now, geometrically speaking, we can do this by using something called the parallelogram rule. I'll show you what that means in just a minute. But before I do, let me remind us some geometric properties of parallelograms. Okay, everybody, let's read through this together. A parallelogram is a quadrilateral, which means it's a polygon of four sides, whose opposite sides are parallel. Number two, the opposite sides and opposite angles of a parallelogram are equal. That's important for us, okay? Remember that opposite sides and opposite angles are equal. And the following is really important. Don't forget this. Adjacent angles of a parallelogram are supplementary. They sum to 180 degrees. That fact is one of the less popular facts of a parallelogram. It's often forgotten, okay? Adjacent angles are supplementary. Okay. Number three, the diagonals of a parallelogram bisect each other, but they do not necessarily bisect the angles of the parallelogram. In some of the applications that we're going to look at, it might be tempting to assume that the diagonals of the parallelogram are bisecting the angles of the parallelogram, but that's not necessarily true. Okay, now let me show you how we're going to use the parallelogram rule to find the sum of two vectors geometrically. All right, look at our first problem. Two forces of 32 and 48 newtons act on a point in the plane. If the angle between the forces of 76, if the angle between the forces is 76 degrees, let me change that word there. There. If the angle between the forces is 76 degrees, find the magnitude of the resultant vector. Okay? All right, ladies and gentlemen, when they say find the magnitude of the resultant vector, magnitude means the length. Find the length of the resultant vector. Now, the resultant vector is found by taking our two vectors and adding them together. Okay? And I'm going to show you how, geometrically speaking, how we take a vector and add another one to it, all right, to find the resultant vector. All right, this is what I'm going to do. I'm going to draw a sketch. So here I have my two my forces, which are vector quantities, 32 and 48 newtons. Okay, so I have this vector here of 32 newtons, and then this vector here of 48 newtons. All right, and the angle between the forces is 76 degrees. They want us to find the length of or the magnitude of the resultant vector. Now, the parallelogram rule is used in the following way. You and I are going to create a parallelogram using these forces, okay, that has these forces as adjacent sides. Okay, so something like this. All right, look what I did, folks. I created a parallelogram, and I said that this side here, opposite this vector, right, by the properties of a parallelogram, opposite sides are equal. So this is also 48. And then this side is opposite the 32 side. So this side is also 32. So there's my parallelogram, okay? Okay, now we know that the angle adjacent to 76 degrees, which is right here, this is adjacent, so is this one, by the way. The angle that's adjacent to 76 degrees is the supplement of 76 degrees. In other words, this angle here will be equal to 180 degrees minus 76 degrees. That is 104 degrees. So now what I want to do is, the next part is super important. I want to draw the resultant, okay? The resultant will be the sum of the two vectors. Now, so what's going to happen is the diagonal of this parallelogram with the same initial point of both vectors. Notice that both, and I did this intentionally, both vectors were drawn so that they share the same initial point. So what I'm going to do is I'm going to draw the diagonal from this common initial point across the parallelogram, and that will be my resultant vector. Basically the sum of my two vectors. So something like this, like that. All right, this is the resultant vector. It's the diagonal. And notice it's one of the diagonals of the parallelogram. And notice that this diagonal here, which I'm calling the resultant, splits your parallelogram into two triangles. So guys, this is the resultant, and they're asking us to find the magnitude, that is to say, the length of this vector, of this resultant vector. But notice now, guys, this is the powerful part. Notice that this is a triangle. A triangle. And what do I know about this triangle? I have this side, I have this side, and I have the included angle. What is that? SAS? So what we can do is use the law of cosines to find x, which I've labeled x here, the length of this vector, the magnitude of this vector. It'll look like this. So what I have here is the magnitude of x. That's the magnitude of the resultant vector, right? Which is the length of the vector. Quantity squared is equal to all of this, which is the law of cosines. Cool. Now all we have to do is, well, first of all, let's punch all this into the calculator and then take the square root of both sides. So punch all that in and then take the square root of both sides, and you'll find to the nearest Newton, to the nearest unit, that the length of the resultant vector is 64 newtons. Isn't that pretty cool? So this problem is done, and I just want to recap really quickly. When you set your problem up, I want you to do it in such a way that you're using the parallelogram rule, which means that you're going to take the two vectors that they name and you're going to place them so that their initial points coincide. And then draw the diagonal from that common initial point across the parallelogram. And that diagonal will be the resultant. And that is the parallelogram rule that I was mentioning earlier. Okay? And then you label this adjacent angle as a supplement of the angle that was given. And then use the law of cosines to find the length of, the magnitude of, the resultant vector. Check out this example, guys. It sounds really interesting. Find the magnitude of the equilibrant of forces of 54 newtons and 42 newtons acting on a point A if the angle between the forces is 98 degrees. Then find the angle between the equilibrant and the 42 Newton force. Now first, let me talk to you about what we mean by an equilibrant. Sometimes it's necessary to find a force, to find a vector that will counterbalance the resultant. Okay? And that's called the equilibrant. And the equilibrant basically is the opposite of the resultant. The equilibrant is the opposite of the resultant. In other words, it's the opposite vector, which means it has the same magnitude but opposite direction. All right, let's sketch a diagram here. And you know what I'm going to do? I'm going to take my two vectors, my two forces, and I am going to place their initial sides so that they coincide. The initial points. Place the initial points so that they coincide. All right, I have my two vectors. I have their initial points coinciding, and the angle between the forces is 98 degrees. What I'm going to do now is form my parallelogram, so I can use this parallelogram rule. Okay, I've created my parallelogram with opposite sides being equal. Now, don't forget that the adjacent angle of 98 degrees is the supplement. So the supplement of 98 degrees is 180 degrees minus 98 degrees. So that will be 82 degrees. All right, now what I'm going to do is draw the resultant. The resultant will be drawn from the common initial point across the parallelogram. So something like this. There's the resultant. Okay? Now, please don't make the false claim that this diagonal bisects this angle. Remember that property number 3 that we talked about earlier? The diagonals of a parallelogram do not necessarily bisect the angles, all right? So do not think that this diagonal bisects 98 degrees. In this case, I believe it does not. Okay, so this is the resultant. This is the resultant. What I want to do now is draw the equilibrant. Now remember, the equilibrant will be the opposite of the resultant. The equilibrant then will have the same length as the resultant vector, but it will have opposite direction. That means the equilibrant will be over here. This is the equilibrant. All right, so that's the equilibrant, all right? Opposite direction. Let me go back to the instructions. Find the magnitude of the equilibrant. Okay, so they want us to find the length of this vector. But you know what I understand is the length of this vector, the magnitude of the equilibrant, is going to be the same as the magnitude of the resultant. The only thing that's different between these two vectors, the equilibrant and the resultant, is their direction. So to find the magnitude or the length of the equilibrant is to find the magnitude or the length of the resultant. So I'm going to focus my attention on finding the magnitude or the length of the resultant, and that will be the same as the magnitude or the length of the equilibrant. Okay, let's use the law of cosines to find this length here. I'll call this length x. All right, so let's use the law of cosines. The law of cosines will look like this. All right, so the law of cosines says this side of this triangle, right? We're looking at a triangle here, SAS, right? This side, included angle, and then that side. This side squared will be equal to the sum of the square of the other two sides minus twice the product of those two sides and cosine of the included angle, or the angle opposite that side, x. Okay, so if you punch all this into your calculator, don't forget to take the square root of both sides, and I'm going to round to the nearest unit. I'm getting that the magnitude of the equilibrant, which is also the magnitude of the resultant, is 64 newtons. So there's our answer for the first part of this question. Find the magnitude of the equilibrant. Okay, so that part is done. Now we're not completely done because there was another part of this. And I'll remind you, if you want to look back at the instructions, that'll be fine. But I'm going to read them to you. It says, then find the angle between the equilibrant and the 42 Newton force. Find the angle between the equilibrant and the 42 Newton force. So find this angle here. I'm going to call it angle, I don't know, alpha. All right, so we need to find the measure of angle alpha. Okay, I'm working over here. Now, one thing I want you to notice is that alpha is the supplement of this angle here. The supplement, basically, of the angle that is formed by the resultant and the 42 Newton force. Now, please do not think that this angle here that I'm highlighting is half of 98 degrees because, like I said earlier, we cannot assume that the resultant bisects the angle 98 degrees. In this case, actually, it does not. The only time a diagonal, by the way, will bisect this angle is if these two forces were had equal magnitudes, and they don't. So this angle here that I'm highlighting, which is the supplement of alpha, is not half of 98 degrees. So our thought process, our strategy is, if I can find this angle, here, let me give that angle a name. Let me call it theta, okay? Let me, yeah, that'll work. Okay, so I called this angle theta. Okay, if I can find, this is my thought process. If I can find theta, I can find alpha. Why? Well, because they're supplements. So let me focus on finding let me focus on finding theta. Once I find theta, I'll subtract theta from 180 degrees to find angle alpha because they're supplements, okay? Now, I think you and I can use the law of sines to find angle theta because look at this. Sine of angle theta over 54 degrees must be equal to sine of this angle. And by the way, this angle is 82 degrees because it's opposite the other angle of 82 degrees, right? In a parallelogram, opposite angles are equal. So sine of theta over 54 must be the same as sine of 82 degrees over x. You see that? We found x to be 64 newtons. So let's set that up. Here I have it. Sine of theta is to 54 what sine of 82 degrees is to 64. Okay? We know this is 82 degrees because it's opposite 82 degrees. And we also know that this length is 64. We just found it using the law of cosines. All right. Then this will mean that sine of theta is equal to 54, right, times sine of 82 degrees. Okay, all that divided by 64. And we can find that theta, you're going to have to use inverse sine, right? Theta is equal to inverse sine of all of this, 54 newtons, times sine of 82 degrees. Make sure your calculator is in degree mode, divided by 64. Okay, and we can find that theta is about 57 degrees. Now that's great because now that I know what theta is, I'm moving my picture up a little bit, all right? Now that I know what theta is, I know alpha, which is the angle between the equilibrium and the 42 Newton force, is just the supplement of theta. So what I do is I will subtract what I just found for theta from 180 degrees to get my answer. Which is approximately 123 degrees, the angle between the equilibrium and the 42 Newton force. Man, this problem was so much fun, wasn't it? Check this out. This is going to be our last question. A ship leaves a port on a bearing of 25 degrees and travels 61.4 kilometers. The ship then turns due east and travels 84.6 kilometers. How far is the ship from port? That's question number 1. And then question 2, what is its bearing from port? Okay, let's draw a picture. All right, I didn't want to show you the complete picture. I want to show you step by step. First of all, the ship is leaving port. This is going to be port for me. All right, and it says it leaves on a bearing of 25 degrees. Now, remember from earlier studies, when they do not give us direction for bearing, it is assumed to be due north, and due north always is always clockwise. All right, so this is going to be due north for us, 25 degrees due north. So the ship is traveling like this. And travels for 61.4 kilometers. And then the ship turns due east. So it's going to start going east and travels for 84.6 kilometers. All right, everybody. So the ship left port on a bearing of 25 degrees due north. And then it went due east and traveled for 84.6 kilometers. All right. The question is, how far is the ship from port? So the ship is right here. The ship is right here. And the question is, what is its distance from the port? All right, so this distance here is what they're looking for. All right, so there's our picture. All right. What I would like for you to realize is we can make a right triangle right here. Right there. This would be a right triangle right there. Do you see that right triangle? And the reason why that's important is because I believe that will help us get this angle here. This angle here. And the reason why I would want this angle here is because if I had it, then I would have this side, and the included angle, basically SAS, and then I could use the law of cosines to find side X, right? The distance that the ship is from port. But in order to get this angle, I think I would have to realize that this is a 90-degree triangle. This is a right triangle, which forces this angle right here. If this is 25 degrees, this is 90 degrees, then what is this? This angle here would have to be the complement of 25 degrees. So that means that's 65 degrees right there. That's what that angle is. I was able to figure out that angle all because I made this right triangle right here. Okay? Now, if this angle here is 65 degrees, then that forces this angle here, which is what I really want, to be the supplement of 65 degrees, which will be 115 degrees. 115 degrees is the supplement of 65 degrees. Do you guys see that? So look at what we have now. We have this triangle, right? And we want to know this unknown side length here. The law of cosines will help me get it. All right, I have the law of cosines set up so that I can find x here. And of course, punch all this into your calculator. And don't forget to take the square root of both sides, all right? And then you should be finding, I did it as well, and you should be finding that you are getting about 124 kilometers. Very good. All right, we did it. That's how far the ship is from port. This is super exciting that we could find that kind of information. The next thing we want to do is find its bearing from port. Now, if the ship is here, then its bearing from port starts right here, due north, and it goes all the way that way. In other words, the bearing of the ship from port will be 25 degrees plus however much this is. Let's call this angle here theta. So that if you and I can find theta, all we have to do to find the bearing of the ship from port will be add 25 degrees, adding 25 degrees to theta. Now, I think we can use the law of sines to find theta, can't we? I mean, look at this. Isn't sine of theta is to 84.6 kilometers what sine of 115 degrees is to x, which we now know to be 124 kilometers. In other words, sine of theta will be equal to 84.6 kilometers times sine of 115 degrees. And then all of that, of course, divided by 124 kilometers, right? That is to say, theta will be exactly equal to inverse sine of what we just said here, 84.6 kilometers. All right, times, so 84.6 kilometers times sine of 115 degrees, and then all of that divided by 124, and you're going to get that theta is about, let's see, punching that in now, and using 3 significant digits, right, is what we're using. Let's see, 38.2 degrees. All right, cool. Now, honestly, our answer's a little off here because we use an approximation in our calculation here. You know, I think this really is like 38.3 degrees, but in order to get 38.3 degrees, we would have to use all of this for that denominator. But let's just leave it like that. All right, cool. Now, this is not my answer. This is not the bearing from port, right, guys? This is just what theta is. I got to add 25 to that. Let me move this up. So my final answer, so for the bearing, it'll be 25 degrees plus theta. So the bearing will be 25 degrees plus 38.2 degrees. So the bearing from port will be 63.2 degrees. All right, that's the bearing of the ship from port.